All right, so I want to, let's see, turn this right side up for you first of all. We're going to talk about a pendulum, and the first thing I want to do is analyze the forces that are acting on a pendulum. Okay, so a pendulum has a string or something. It could be a solid rod, doesn't matter. Let's get origin. And then at the end, this massive thing is called the pendulum bob, like a plumb bob or whatever. We don't have anyone in class named Bob, sadly. But for most problems, we're going to assume that whatever is holding the bob is massless, and it's attached to some solid thing up here. And the pendulum will usually be specified by a length. You could use L for that, or sometimes use R. And then this will have some mass, M, which may or may not be told to you. Okay? And if it's just hanging there, if it's just in this position, then it's in equilibrium. And what we just learned from the lecture last hour is that the tension in the string is just going to equal the weight of the pendulum bob. But that's not a very interesting harmonic oscillator. So let's look at it when we displace the pendulum bob from its equilibrium position. Let's look at what the forces are on the bob when it's in this position here. Okay, so we've displaced it by some angle theta, and let's analyze the forces that are acting on it. So we've got mg downward, and we've got a tension in this direction, and this angle right here is theta. So
hey Doc.
Yeah.
So Devlin said Shiloh's waiting to be let in.
Oh, sorry. Thank you for letting me know. I don't see her. Tell her to ask again, because it didn't come up on. Maybe she's going to the other Shiloh. Maybe she went to the other class, or to the other hangout. Let's see. Tell her to go to the hangout that is... Okay, she's trying again. Devlin, she needs to make sure she's going to the hangout that was posted in Classroom for our 1 o'clock meeting, not the meeting at 12. I probably should have just recycled that. Okay. I'm sitting on the screen right now waiting for her request. All right. Well, while I wait for that, let's do what we did. There we go. Okay, Shiloh, welcome. What we're looking at is a pendulum, and it's got a bob on the end of a string, a massless string. We drew a free body diagram for the bob, which has tension pulling up and to the left and the weight of the bob pulling down. And now we can write this in terms of the components of the force. Now we should think about what is tending to make the pendulum move back towards its equilibrium position before we draw components. And that is a tangential force. Okay? We have a radial force, along a radius, and this is called a tangential force because it's at right angles and it's along a tangent. So if we look at it this way, then we'd like to take the gravitational force and look at its components, not the components of the tension, but the components of the gravitational force. So we'll put our axes this way, kind of like we did for something on an inclined plane. And in this case then, if we redraw the free body diagram with components, we'll have tension still going this way. We'll have a component of the gravity going this way and a component of the gravitational force going that way. This angle here is theta, so this is mg cosine theta, and this is mg sine theta. All right. And what this tells us is that the tension is going to be mg cosine theta. So the tension is going to vary as we move this pendulum to different angles, but as long as we don't exceed the strength of the string, well, actually it's maximum when the bob is at the bottom, because the angle is 0 there and cosine of 0 is 1, so that's the maximum, and the amount of tension diminishes, and when we get all the way up to a 90-degree angle, there's no tension at all in this string. The restoring force, the force that is trying to make the bob go back towards equilibrium, is mg sine theta. We call that a restoring force because it's trying to restore equilibrium. And that's the same term that we used for the force in the mass spring system. The spring force is a restoring force. Okay, so I said yesterday that for simple harmonic motion, the necessary condition is you need a restoring force that is proportional to displacement from equilibrium. In this case, our restoring force F is equal to mg sine theta, and theta really is the displacement from equilibrium. When the angle is 0, we're at equilibrium, and then as we move the bob to the side, theta is changing. So we're going to make an approximation here. I want you to try this in your calculator. Sine theta is approximately equal to theta for small theta. Now, the argument of the sine function must be dimensionless. So if you try to take sine of 10 degrees, degrees has a dimension on it. You have to express theta in radians. By the way, this is background. You know, you don't need to know this, but you might like to know where the equation comes from. So if theta is in radians, then, so if you put your calculator in radian mode and look at the sine of theta, you'll find it's very close to the theta that you put in. Let's see if I can, well, I don't have a calculator right here handy, but let's look at the graph of the sine function. Right, sine starts at 0 and goes up. Well, in the very beginning, it follows the sine of theta, follows the line y equals x, or it follows the theta line. So for small angles, they're going to be approximately the same, and then the sine function is going to bend away, and sine theta will be smaller than theta for larger angles. And this works well. You can verify this for yourself, but it works well for theta less than, say, about 10 degrees. I mean, the smaller the angle, the better the approximation is. If you're exactly theta equals 0, it's perfect, because the sine of 0 is 0. As soon as you move away from 0, it's an approximation, but it depends on how good you need to be. Okay, so now we have the force is equal to mg times theta, when theta is in radians. I would say approximately equal here. And so then we can have simple harmonic motion. Okay, so the pendulum swings back and forth. It's going to have a period and a frequency, which is 1 over the period. And it's going to depend on certain things. What I think we'll do is a little experiment. I'd like you to try this at home, because a pendulum is easy to make at home. You can just take a paper cup and some string and a paper clip, so you can make your bob out of the paper cup. Hook a paper clip to it, tie a string, and you can vary the mass here. You can put, say, coins or water or something like that, and you can vary the mass of the bob. You can also vary the length of the string. And I guess the other thing that you could vary is the initial displacement, how far out you pull it when you let it go. And so for yourselves, I think this is a very important experiential exercise for you to do, and not hard to do. I'd like you to measure the period the same way we did yesterday with the mass spring system, or the mass rubber band system. Let the pendulum go 10 times, and then take 1/10 of that for the period of one complete oscillation. And you can try varying the mass, the length, and the initial displacement, or what we call the amplitude. How big a swing is it? Okay, so I have a little pendulum set up over here. I'm going to flip the camera around. Let's see how this works. I don't know if I can zoom out. Probably not. There, I'll zoom out by stretching. Okay, I realize it's kind of brightly backlit, but hopefully you can see. So this is such a heavy mass, I have to hold it. But you can measure 10 oscillations of this. I'll let it go for 20, starting now. Okay, so hopefully someone was able to record. Let's look back and see what we got. Put down a little paper again. And did anyone record the period of that pendulum? You can type it into the comments. No one? Okay. So, or 1.3. Caught you, yeah, I did. I caught you all slacking. Should we do it again? Yes. We'll do it again. Get your phones out. Yes, we're doing a demo. We got to go back to another screen. Okay. Got your phones. Here we go. Let it go 15 times this time. Okay. So hopefully you got that. And I just realized I can put on my headphones. Maybe get a better microphone out of this. All right, I'm here now. And now those numbers are coming in. 0.12, 0.12, 0.12, or no, 1 point, okay. 11, yeah, so it's 1.2 seconds roughly. Okay, and Gabe was watching us. That's okay. Oh my gosh. Hope I didn't hurt anyone. All right. Okay, so we have 1.2 seconds. Now, what do you think will happen if I shorten the string? Will the period go down or up? Devlin thinks it'll go down. Okay. I want to know if I shorten the string, is the period going to increase or decrease? Will it swing faster? That's a decrease in the period. Or will it swing more slowly? That's an increase in the period. Okay, so it's going to go more slowly, Evan thinks. Audrey says down. Okay, so now I shall shorten the string, tying a new knot. Maybe I can actually, before I do that, I'm going to measure, if I have a ruler handy. Probably have a ruler in one of these drawers here. Oh, I know, I took that ruler at Tutor. All right, we'll use a piece of paper as a ruler. So this is 11 inches, and from here to here, and then about another, I'm going to go to about the middle of this weight, because that's where the center of mass is. That's probably about another 4 inches. So we'll say it's 15 inches. All right. So I wrote that down. Now we'll shorten this guy. can see that. Maybe you can hear my dog, I don't know. All right, let it go 20 times before. Okay. Now maybe you could see pretty well how long that was taking. See what you got for me here. So before we were at 1.2 seconds, and this time, did it go to 1.0 or 0.10? It did go down. I think 1.0. All right. And we'll estimate the length of this with our handy dandy piece of paper. All right, so that's 8.5 to kind of the top there, or 11. I should go from here. 11 minus, those are 1/4 inch. 1, 2, 3, maybe 10 1/4. More or less. So, we made the length 2/3 of the original length. The time did not go down by, it's not 2/3 of the original time. That would be 0.8 seconds, right? So, we know that the period is somehow inversely proportional to the, no, it's proportional to the length. It's a longer period, length is in the top. Okay. How about the effective mass? What do you think will happen there? If I change, I've got the heavy mass. Wait, whoops. Speech 100. Whoops, Doc, look at my comment. Wait. Am I not being heard? Can you hear me? "15 inches is 1.2 seconds, I think, not 0.12. Because 0.12 would mean like 8 per second. Okay. All right. Y'all with me? So, longer string, longer time. Shorter string, shorter time. And now I want to know, what do you think will happen if we add a greater mass to the pendulum? So, if we go from existing mass there to this big guy. That was a kilogram, and this one is it's probably 2 kilos or something. It's really heavy. I have to hold the ring stand so it doesn't pull it over. Okay, so predictions. No change. Devlin says no change. Everyone else is chicken shit. Oops, chicken. Everyone's chicken. I did not say a naughty word. Okay, here we go. That's your timer. Take that off. Okay. Devlin says it was just under 1 second, 0.99 seconds. So this is with 1 kilogram, and then with the heavy mass, I don't know what it is. I'm going to say 2 kilograms. It was also 1 second or 0.99 seconds. Okay, so no change with the mass. Why is that? Well, if you think about it, the amount of force that's acting on the bob to restore it, this restoring force, mg sine theta or mg theta, is increases with the mass, right? Force goes up as you increase the mass. But the inertia of the pendulum bob also goes up as you increase the mass. So the amount of acceleration and therefore its motion all becomes independent of mass. So the mass cancels out. So the formula we're going to end up with, which should be on the equation sheet, is going to be, it's going to look kind of similar to what we saw for the mass spring system. The period is going to be 2 pi, again because we're looking at an entire cycle, one time around the circle if you want to think of it that way. And then it's going to be L, the length of the pendulum. Use capital or lowercase, I don't care. I think I usually use lowercase, but for some reason I wrote capital. And then the other piece is going to be the acceleration of gravity. Now let's look at the units here. L over g. Length is measured in meters, and acceleration is meters per second squared. That is the same as meters times seconds squared per meter. Meters cancel. Uh-oh, that gives us seconds squared. That's not a time. So we need to have a square root there. Okay? So with our approximate experiment that we did, we had 1.2 seconds for about 15 inches, and we had about 1 second for about 10 inches. And so the length was 2/3. So what is the square root of 2/3? Pull up my calculator here on my computer. 2/3 square root 0.82. Okay, what's 0.82 times 1.2? 0.979, or close to 1. So square root of 2/3 times 1.2 seconds is about equal to 1 second. In other words, the physics works, and our estimates, my estimates of the length weren't too bad either, estimating where the center of mass of that pendulum bob was and so forth. So I think that's mainly it for what I wanted to show you about the pendulum today. On Monday, I'd like to look at both a mass on a spring and a pendulum. As it's moving back and forth. And I want to look at how does position vary with time, how does velocity vary with time, how does acceleration vary with time, how does force vary with time. And then we can also look at kinetic energy and potential energy. All of these are going to be cycling back and forth, and we want to see how each one of those varies as a function of time. As the mass is moving back and forth, the position goes, you can call that negative as it gets closer, and then it goes positive. It goes through, call this 0. The equilibrium position is always 0. So here, this would be 0, angle of 0 degrees. Okay, so think about each of those. Think about the force, because the force and acceleration are going to go the same. Do you remember the formula for the potential energy of a spring? I'll remind you. You probably do remember. Since I can't hear you, I'm going to assume that you're all just saying it out loud. It was 1/2 k x squared, where k is the spring constant and x is the displacement from equilibrium. Okay, so think about those things, make the little toy, play with pendulums, and we'll get back on Monday. Okay, now I'd like you to unmute. I'm going to stop recording this